Good morning, everyone. I'm Kelly, and I work with music and audio app developers to help them launch and build successful businesses on Google Play. We're really excited to be here today to share with you both technical and business best practices for developers that require high-quality audio. So our session is divided into 3 parts. I'm first going to share with you tips from leading audio developers who have successfully built businesses on Android. Then Dawn is going to join me on stage to share common technical hurdles that audio developers face and ways to overcome them. Then Phil will be announcing our latest A-Audio framework that we think will help developers reach your performance needs. Then to wrap things up, we'll have Roland, Rolly's CEO, join us on stage for a really cool live music demo, so stick around. So I grew up in Los Angeles, California, in a very musical family. And I remember the first time I stepped foot into a music studio. It was really exciting, but I was also a bit overwhelmed by the amount of professional tools and expensive equipment, and not to mention that renting the music studio itself wasn't exactly affordable. As a teenager, these DJ turntables were my favorite piece of equipment because I thought it was pretty cool being able to mix my favorite beats for my friends. But as cool as these turntables are, having access to expensive equipment or an expensive studio isn't really feasible for most people. So luckily, for the billions of people around the world who want to produce music, music creation has changed drastically. Now, with the accessibility of mobile, you can simply download an app and have pro-like quality music instrument and a music studio directly in your pocket, making these DJ turntables accessible to everyone on their phones. And that's why we've seen tremendous popularity in apps like eDJing, with over 45 million installs. But of course, it's not just DJ apps that have grown in popularity. It's apps that allow you to sing karaoke, such as Smule Sing, with over 52 million monthly active users, and apps like Chord K-Oscillator that recently released on Android. And while high-quality audio is important to music creation apps, it's also important to a whole host of other apps, such as VR or voice-reliant apps or games. And the market for high-quality audio apps is only expanding. So that's why I'd like to now dive deeper into the first part of our agenda, which is sharing with you 3 best practices from leading audio developers who have successfully launched and built their businesses on Google, Android. These best practices are launch smart, think global, and everyone's favorite, make more money. So first, launch smart. So we know that device fragmentation on Android can be a major challenge for developers that require a high-performance audio. In order to deliver the best user experience, it's important to understand what device work well for your performance needs. By performance here, I'm specifically talking about a device's CPU and latency. With the lower the latency, the better the user experience. So let's take a look now at how JoyTunes, an app that requires low latency, approached launching on Android in order to maximize their reach but still achieve a good user experience. So JoyTunes is the creator of Simply Piano, a subscription-based music app that helps users learn how to play piano. In fact, my daughter here has learned how to play piano almost exclusively on this app. So we've had a piano in my household her entire life, and it wasn't until I introduced her to this app that she think that playing piano was all of a sudden fun. So what she does is she simply follows along to the guided lessons on our piano, and the app immediately recognizes what she's playing and then provides feedback to her to help her improve. So the key here is that when my daughter presses down on the piano keys, she expects that Simply Piano will immediately and accurately hear what she's playing and provide feedback. But in order to have this experience, Simply Piano requires low latency of playback and recording of musical tracks. So to figure out what devices meet their low latency and computational performance needs, they first launched a beta version of their app in our Early Access collection. So Early Access is a collection on Google Play for new selected apps that are still in beta. Inclusion in this collection enabled JoyTunes to build a beta audience and to be able to collect private user feedback. This enabled them to identify both problematic devices where users were having a poor quality audio experience, but also problematic regions that they were then able to exclude from their production version. They also developed a way to have their app work on lower-end devices by making automatic adjustments of certain features, such as changing and optimizing the graphics so that a user on a particular device would still have a good experience. So with all of these learnings, JoyTunes was able to then launch to a public audience with a very high user rating of over 4.3, and to also launch to a larger number of devices than they had originally thought possible. So second, you want to think global when you think about launching your app or growing your user base. And Android has tremendous strength here, and we continue to see enormous growth of music creativity apps in both developed and emerging countries. When expanding to developing regions, though, you want to optimize your app for its specific needs for users that are in that market. For instance, you may find that there's a higher number of users that are on low-end devices, and you may find that more users have lower bandwidth constraints. But as mentioned with Simply Piano, you don't have to limit your app to particular devices. There's a number of technical things that you can do to optimize your app for both high and low-end devices. So let's take a look now at another leading audio developer that has been distributed globally, but has seen enormous success in emerging markets. So Smule is a leading developer of mobile music apps, including Smule Sing, that allows users to sing along to their favorite songs in a karaoke-style fashion. So for instance, if I wanted to sing, or if any of you wanted to sing Disney Frozen's Let It Go, the app would match up what I am singing in real time with the song, and then I'd be able to overlay audio graphics to make my humble voice sound like a pop star. If Disney sing-alongs aren't popular in your household, they have a ton of other genres too. So Smule has seen phenomenal growth, but last year, the app saw over 10x active user install growth in the Southeast Asia region, with over 40% of their user base now comes from this region, with Indonesia being one of their fastest growing countries. But not only have they seen enormous active user install growth, they've also been monetizing well there. So with over 7x increase in revenue over the same year in the Southeast Asia region. So in addition to some of the technical optimizations that they've done, another reason for this viral uptick can be attributed to Smule offering locally relevant content. For instance, a user in Indonesia, pictured here on the left with the headphones, can sing along to one of the world's top hits, or she can choose to sing in a duet-style karaoke with one of her favorite regional artists, such as Sita, pictured on the right, who's a very popular Indonesian singer. So as you think about expanding your reach, you want to identify areas of growth and then create a localized experience for that market. I also encourage you to check out our Building for Billions guidelines online if you're interested in more tips on building for emerging markets. Lastly, you want to ensure that you're testing your monetization strategy to achieve the best business results. So many music creation apps have historically required that users pay a premium price in order to access their app. But because of the variety of payments that are available on mobile, user consumption habits have changed. And in fact, on Play, our fastest growing business model comes from subscriptions, where we've seen both subscribers and revenue double over the last year. So while the last two apps that I mentioned, Simply Piano and Smule, allow users to download the app for free and test it out and then sign up for a subscription, the developers of Ultimate Guitar Tabs have tested an interesting hybrid model. So Ultimate Guitar Tabs allows you to learn how to play guitar through in-app lessons, or you can just jam to your favorite song. So Ultimate Guitar started off as a premium app, but rather than charging a high price point, they experimented with a lower price point for a paid app, allowing users to download the app for $2.99, as you can see on the left. This essentially lowered the barrier to entry. Then they upsold their users once they were in the app, allowing them to download the full version for $9.99, as you can see on the right. So this hybrid approach of using paid and in-app purchases turned out to be an effective monetization model for Ultimate Guitar Tabs. They not only increased their revenue overall, but in-app purchases now account for 65% of their revenue, which is a pretty striking stat given they're already a premium app. So while a hybrid approach worked for them, I encourage you to test out different monetization models beyond premium and see where you have the best conversion results. So these are just a few examples of audio developers that are seeing tremendous success on Android. There's a tremendous appetite for music creativity apps, And so we think if you follow the business tips that I just gave, and also some of the technical tips that Dawn and Phil will be sharing, that there's a big opportunity for developers in this space. I would now like to introduce Dawn to the stage to discuss common technical hurdles and how developers can overcome them. Thank you.
Hello, hello. Thank you, Kelly. Hi, I'm Don. I'm a developer advocate, and I lead our developer efforts for the Android high-performance audio framework. What that means is I help you guys create amazing audio experiences on Android. What it actually means is I spend virtually all my time listening to sine waves. Outside of Google, I do a bit of DJing, and in my head, I like to DJ in places like this. But the reality is actually probably closer to this. More people definitely turned up later, I promise. OK, so today I'm going to give you 2 best practices which you can use in your apps to create amazing audio experiences. These are obtain low latency audio paths and meet your audio deadlines so you don't give your users headaches by putting audio glitches into their ears. So starting with obtain low latency paths. I'm going to talk about 2 signal paths through the Android system. Number 1, recording, and number 2, playback. Now, one of the first questions that I often get from developers is, what is the latency of this path? And this is the thinking behind the audio.pro hardware feature flag. And if a device reports support for this flag, it means that this particular path is less than 20 milliseconds over the headset. You can use this flag in your app to either enable certain features, such as live monitoring, or you can only distribute to these devices, these pro audio devices. And there's now tens of devices in market which are supporting this particular standard. So it's not just Pixel and Nexus devices. We're seeing good uptake from OEMs as well. So audio recording. This is the path through the Android audio framework when you're recording. You have an analog signal into a microphone, goes through an analog to digital converter, through some effects to kind of clean up the signal. This can be things like noise cancellation and echo cancellation. And then the digital data is delivered to your app. Now, effects can add latency So if we're talking about low latency apps, what we want is the lowest possible latency. And there is a route through the system which allows us to avoid adding this latency. And this is obtained using the voice recognition preset. The other thing we need to remember here is to use PCM16 format. And this essentially allows the audio framework to not do any format shifting, which potentially could add latency. So that's all I'm going to say about audio recording. Audio playback is a little bit more complicated. So every phone that produces audio in the world has a digital to analog converter in it. This takes ones and noughts and converts it into a voltage, which is used to drive headphones or a speaker. Now, I like to think of this as kind of a character, which is chomping down on this audio data and producing the signal. In fact, I even have a name for him, DACman. Now, DACman has very specific requirements for his food. He wants it served to him at a certain rate, and he also wants it served to him in bite-sized chunks of a very specific size. Now, for this analogy to work, DACman also includes a DMA controller and all the other hardware required to consume audio, so just bear with it. So this is how DACman fits in to the Android audio architecture. So your app is at the top here, and it's your job to get your audio data to the output as quickly as possible. The default path through the system is to go through a resampler, through some effects, again, to improve the acoustic quality of the signal, and then through a mixer and out to DACman. Now, as with the recording path, the resampler and effects will add latency. And we can obtain a lower latency path called the fast mixer path if our app conforms to certain requirements. So, number one, we need to obtain the correct sample rate. So remember I said DACman wants his food at a specific rate. We can use the Audio Manager API to find out exactly what that rate is. And that will enable us to create an audio stream on this fast path. The other thing we need to remember is not to add any effects. So once we've created this audio stream to DACman, we need to start supplying audio data. And we need to do it in this specific chunk size. And again, we can use the Audio Manager API to obtain this optimal size. So after this first chunk of audio data is consumed by DACman, he sends us a callback. He's basically saying, I've run out of food, feed me more. And we get this callback on a high priority thread, and this allows you to do your audio processing work without being preempted by other parts of the system. Now, this is a fairly critical part of any audio app. So let's take a closer look at what happens inside this callback. So every callback has a deadline. Remember that you have to send these chunks of audio data at very specific intervals. So the amount of time you spend in this callback is going to vary based on the computations that you're performing, like the complexity of the audio data, but also CPU frequency and the device that you're running on. If you miss this deadline, DACman is going to be very unhappy, and he's going to output silence in protest. So it's very important that we don't miss these deadlines. So for the next part, I wanted to talk about some common reasons why you might miss these audio deadlines. So starting with blocking. So inside your callback, there are various reasons you might block. And here I have a code sample which does a whole lot of bad things you shouldn't do in your callback. So number one, logging. Instead of logging inside the callback, you should use atrace and use systrace. It's a much better tool for debugging the callback. Don't do memory allocation. If you need to use memory inside the callback, which invariably you do, you should allocate the memory up front when you instantiate your audio stream, and then just use it inside here rather than trying to allocate new memory. Don't wait on other threads. Bear in mind, this is a high priority callback. So if you're waiting on a lower priority thread, you have priority inversion. Don't do file I/O. If you need to read from a file, use another thread and then use a non-blocking queue or a circular buffer to transfer data into the callback. And don't sleep. There should never be any need to sleep inside here. So we've dealt with blocking. The next reason why you might miss your deadlines is core migrations. Now, when you create an audio app on Android, the CPU scheduler will assign your audio thread to a particular core. And here I have a systrace, which is showing the audio thread running on CPU 1. And we have 4 callbacks marked in those green rectangles there are the callbacks. The other row of interest is fready1 here, which shows us the state of our audio buffer. And we have 4 callbacks, and then the CPU scheduler shifts our thread over to CPU 0. Now, this core migration can incur a slight time penalty in the order of a few milliseconds. And this can cause our callback to start late and therefore run over. And sure enough, we have an audio glitch occurring there. So the solution to this is to set thread affinity, which means that we can bind our audio thread either to the current core which we're assigned. That's like an OK way of doing it. Or we can use get exclusive cores on API 24 or above in order to get the cores which are reserved for the current foreground application. Right, lastly, CPU frequency scaling. So this is a process which is used to give users great performance and great battery. It's like a power-performance trade-off. CPU frequency is high when users need good performance, and low when they don't need good performance, but they do want to conserve power. So this is great for most applications, but for real-time audio applications, it can cause a problem. So imagine you have a synthesizer app, and every time you press a key, the synthesizer app generates a voice. This is how the computational graph might look for an app like this. So we start off, we have 10 fingers down on our keyboard, and app bandwidth required is fairly high. Now we take our fingers off that keyboard. Our bandwidth required drops down, and the CPU governor sees that actually our app doesn't need as much bandwidth, so it drops down the CPU frequency. Everything's fine so far. Now we put our fingers back on the keyboard. Our bandwidth rises to its previous level, but the governor takes a while to ramp the CPU frequency back up to the level that we need. So unfortunately, during this time, glitches are occurring. So the solution to this, well, the title of this talk is Best Practices for Android Audio, but for this section alone, let's just call this Don's Practices for Android Audio. And this is from working with top partners like Rolly. This is what actually works in the real world. So what you can do is you can use something called stabilizing load. Now, the idea here is that instead of having a varying amount of time spent in your callback, you have a fixed amount of time. And this stabilizing load can be things like gating voices on and off, or you can use assembler no operation instructions, basically to keep the CPU spinning. So the result of that is that you basically have fixed load, fixed CPU frequency, and you always have the bandwidth you require in order to generate audio data. This is best used with sustained performance mode on API 24, as this will avoid you running into thermal throttling issues. So in summary, obtain low latency audio and always meet your audio deadlines. I'd now like to hand over to Phil, who's going to talk about a fantastic new audio API in Android. Welcome, Phil.
Okay, thank you. Hello, my name is Phil Burke, and I work in the Android audio group, mostly on MIDI and pro audio applications. My background is in experimental music, so my personal goal is to make the Android platform really a great platform for making strange kinds of new musical instruments. So that's sort of what motivates me. What I'll be talking about is a new audio API called A-Audio, which we're very excited about. And then I'll show you how to do callbacks using that API. And then I'll also show you how to optimize your latency on any particular device you happen to be running. So A-Audio is a C API, so this is a native API. You may be wondering, why a new API? We already have OpenSLES and Java. And the reason is that A-Audio is, we think, easier to use. And if you've used OpenSLES and compare them, I think you'll see why. Also, it's a platform where we can make improvements. And this will show you how we do that. These three APIs can all go through the existing Audio Flinger framework. But if we make radical changes in the Audio Flinger, we potentially could break thousands of apps that are already existing. So what we do is we add a new A-Audio service where we can do some pretty radical things and not have to worry about breaking existing stuff. So we can do some big performance enhancements in the A-Audio service. So A-Audio uses the concept of streams, audio flowing from the mic to the app, back down to the headphones. So how do you create a stream using A-Audio? We use a builder design pattern. So in the builder, you can set your parameters that you want. You could leave everything just the default, and you'll probably get a stereo output stream. But if you need a specific sample rate or a specific format, you can set that. Once the builder is set up, you can use it like a rubber stamp to create multiple streams. So this is what it looks like in the code. So we have A-Audio, create stream builder, pretty straightforward. And if you want, here's how you set different parameters on the stream builder. Once you've set up the stream, you call Audio Stream Builder open stream. Again, pretty straightforward. And then if you didn't specify things like the sample rate or the format, then you'll need to query it to find out what you got. Don't just assume that it's 48,000 hertz, because some devices, particularly like USB devices, it might be at 96,000 hertz or something. So it's important to query to find out what you really got after you open the stream. Another important value is this frames per burst, and this correlates with the chunk sizes that DACman was consuming in Don's slides. So what is a burst versus what is a buffer? There's this can be very confusing. So when we say buffer in A audio, we're talking about the whole array where the audio data is stored for a particular stream. And in that buffer, there can be multiple bursts. So in this case, DACman has 2 bursts that it can consume, and we're writing in the size of a burst. You have to start your stream. You can pause it, you can flush the stream, stop it. These are asynchronous calls, and normally you don't have to worry about that, but if you have to synchronize, we do have a function that will allow you to synchronize with a state machine inside A audio. The reading and writing. So we have to get data in and out of these streams. So there's 2 ways. If your application doesn't need super low latency, the easiest thing is just to read or write using blocking writes. And so here we're in a loop and we're doing a write, and you notice we have a timeout there as a last parameter. When we do a blocking write, we'll get back either an error code or the number of frames written. And if it times out, or if we use a timeout of 0, it may not be, we may get a partial transfer. Okay, the second technique is when you need the lowest latency. And to do that, you'd need a high priority thread that may be running with a SCED FIFO scheduler, and hopefully at a higher priority as well. So the way to do that is to write your own callback function. So this is a function that you would write, and A audio will pass to you a stream parameter, a user data, which could be an object or a structure pointer, and then audio data pointer, which is a pointer to your array and the number of frames, and then you can render directly into that audio buffer and then return. Once you have defined your callback function and you know what data you want to pass, you give it to the builder, you set the data callback on the builder, and then when you later create a stream, it will use those values. Sometimes people need to combine multiple inputs. Maybe you're taking 2 input sources and mixing them and sending them into an output. So what's the best way to do that with A audio? We recommend using 1 stream as a master and doing your callback from that master stream, which ideally should be an output stream. And then what you do in the callback, see here we're being passed the output stream pointer. So what we do in the callback is we do a read from the input stream and we set the timeout to 0. So this is a non-blocking call. As Don mentioned, you don't want to block inside the callback. Now initially you may not get all the data that you're expecting, but pretty soon these 2 streams will synchronize like very quickly within a couple buffer calls, and then you'll have nice back and forth between these 2 streams, and you can do echo or guitar effects, things like that. The other topic I want to discuss is dynamic latency tuning. So if you, it's very difficult to predict ahead of time what the exact number of buffers that you need, and the number of buffers determines your latency. If you have too few buffers, too few bursts, I guess, in your buffer, then if your thread is preempted, you may glitch. So what you want to do, if you look at this diagram from before, right now we only have 2 bursts that are valid in this very large buffer. So that's our latency is 2 times this burst for this buffer. So if we are unable to write to the buffer, DACman will run out of data after 2 bursts. So if we have a glitch, we may wish that we have 3 bursts in the buffer, so we have a little bit more cushion if we get preempted, if our thread gets preempted. So we can adjust this value. The way you do that in code is that you can query to find out how many overruns or underruns you've had on that output stream. And if it's changed since the last time you checked, that means that you just had a glitch. So what you can then do is you can query to see what the size is of the buffer, basically how much of the buffer is being used, which determines your latency, and then bump it up and say, well, let's just add 1 more burst in here. So instead of being double buffered, I'll be triple buffered. And then you set that back in, reset your size. So this is a sort of a simplification. You may find that you want to, if you could do timing analysis and maybe lower the latency again later if you haven't glitched for a long time. But that's up to the application to do those kind of smart smart analysis. But this is the basic technique. So in summary, to a minimal audio program, you create a builder, you open a stream, you start the stream, and then in a loop, this case we're doing the blocking writes, synthesizing audio and writing it to the stream, and then we close it when we're done. So pretty simple. Just for comparison, this is sort of an equivalent OpenSLES program. It's probably a little hard to read, but as you can see, the A audio is fewer lines of code, a little more straightforward if you want to use audio. So now A audio, you're probably thinking that sounds great, but it's only in the O release. So how does that help me if I'm writing for Marshmallow or Nougat or Lollipop? So what we're doing is we're developing a wrapper which has is basically like the A audio API and A audio features, but it's in C++, so it just looks slightly different. And what we do is we dynamically link to the A audio library using runtime linking. So your program can run and link on previous versions of Android, but A audio won't be there. And so then what we do is we just dynamically switch over to using OpenSLES. So if you write your program to this new API, which will be like an open source thing, where it's not quite out yet, but it will be out soon. Then if you write your program to this C++ wrapper, then you'll be able to use A audio or OpenSLES transparently and run on old or new platforms. Okay, I'm excited about what's coming up next. This is Rolly is going to give us a demo. And Rolly is a company that's been taking advantage of a lot of these tricks. They've figured out a lot of stuff, and they've been a great partner for us. So I'd like their CEO of Rolly, Roland Lamb, to come up and give us talk about some of the programs they've been developing on Android. Thank you.
Good morning, everybody. It's such a pleasure to be here. As Phil was saying, I'm Roland Lamb. I'm the founder and CEO of Rolly, a company that is developing new musical hardware and software. And I'm very pleased to have Marco and Jack Parisi with me, who are virtuoso musicians who are kind of on this cutting edge of new hardware, new software, and expression. So just to give a little bit of background, starting out, I felt really passionate about creativity and about the joy that comes from creation. And in particular, we thought we want to empower everyone to be creators, but particularly in music. And the reason for music being kind of the center point for us is that there's this huge opportunity for expression that is untapped. And the way we think about that is that musical instruments are tremendously expressive, but they're still quite difficult to learn. And on the other side, electronic music has such versatility associated with it, but then it's relatively technical still and complicated to set up your own home studio. So we thought, what if we could create instruments that were deeply expressive, but also easy to learn, had the versatility of electronic music, but then didn't have all of the extra technical setup. But to solve that problem, we thought, first of all, we need these high-resolution control devices for digital. So, we couldn't, if you just have like simple one-dimensional electronic controllers, you can't get to that depth of expression that you have with all of the physical gestures you can create with acoustic instruments. So I invented this instrument called the Seaboard, and the Seaboard is an evolution of the piano keyboard. You can play it just the way that you play a piano, but then you can modulate all of the sounds in real time using very intuitive gestures. So as Marco will show, you could play the Seaboard, first of all, just like a piano. I think maybe if the guys can bring up the audio. Sounds like maybe they just did, Marco. We're running the Seaboard now on Pixel. Take it. It's kind of like electronic piano patch. He's just playing it like a piano. But if he wants to, he could play it, for example, like a guitar. And he would just be able to bend these soft silicon keys left to right, as you'll see. So those kinds of bends that usually you would associate with another kind of acoustic instrument, you can create in this context. And there's many, many sonic possibilities with something like the Seaboard. So we thought, wow, this is awesome. We have this new physical technology, but we want to make it as accessible as possible, to reach many, many more people around the world. So we built a new product called Blocks. And Blocks takes the technology of the Seaboard and puts it into a format of a small, like pocket-sized music controller. And you see it there. You can use it to just play beats or play expressive melodies. And when we launched Blocks, we initially launched on iOS, but the idea was always to make it, go far and wide. And so the issue for us was really about the latency, all the stuff that Don and Phil have been talking about, because to power these new expressive instruments, we developed a professional-grade synthesizer called Equator. And with Equator, you're running many, many different channels of synthesis at the same time, and you're controlling them with all of these different multi-parameter gestures. It's a professional audio application that's used in studios all around the world. So to run that on a phone, we had to do quite a bit of work, but the recent developments in the last few versions of Android have made a big difference, and all of the stuff that's just been discussed has actually made it so now we can run all the sounds in Equator on Android devices. Noise, the application, is available in early access in the Google Play Store. And Marco and Jack, some of you may have noticed, opened up Google I/O 2 days ago with a performance that was performed just on 4-pixel phones. So they're going to just play a minute from that. So it's Seaboard plus Blocks plus 4-pixel phones, 3 instances of noise, and they're also using DJ Pro 2. So let's take a look. Thank you so much. So one of the reasons why we were able to do this was that we developed a coding framework called Juice, J-U-C-E, and it's a C++ cross-platform framework that's built for audio, and it's really built for speed. And so we've been working not only using Juice for noise, but we work with thousands of developers around the world who are creating audio applications that are cross-platform. And what we're finding is with these recent improvements in Android, it's not just for our applications, but for many of our developers, they can take applications that were audio applications that were developed for iOS, for example, and now port those over to Android. And we're also seeing this is an interesting opportunity for a lot of other developers out there who want to create low latency audio applications, but don't necessarily have the resources to learn all of the different systems associated with the different platforms. So that's something to check out if you're interested at juice.com. We also organize something called ADC, not the ADC that Phil was talking about, but it's called an Audio Developer Conference in London, which is on the 13th and 15th of November, which is, deals with all of these issues. So check that out at juice.com. But just thank you for tuning in, and we thought we'd leave you with one more little performance from Marco and Jack. So Marco and Jack Parisi, everyone, and also check out their work. Parisi is doing some amazing things and releasing some great work. So I believe that's all for this session, and there's a sandbox that will follow. So come check it out, and thank you all so very much for coming today.